Let's talk a little bit more about laminar flow. Laminar flow is described as steady and incompressible and constant. It is fully developed in straight circular pipes. So all those things make up laminar flow. If I'm looking at a side view of my pipe here with laminar flow, I've got this lovely parabolic curve forming inside here, and I'm going to have an average velocity somewhere in the middle here, making this peak point right here my maximum velocity. In laminar flow, the maximum velocity is about 2 times the average velocity. When we were talking about Bernoulli's equation and the energy equation, we kept talking about pipe head loss. And up to this point, we've been giving you the head loss. Well, now we're going to talk about calculating it. So if I have a 0.1 here and a 0.2 here, I can have a change in pressure from 0.1 to 0.2. This is assuming my average velocity going on here and the diameter of my pipe here. Our change in pressure would be pressure 2 minus pressure 1. And for laminar fully developed flow, that's going to be 32 mu times the length and the average velocity, all divided by the diameter of the pipe squared. A couple of notes: pressure drop due to friction is irreversible. We can add energy back into the system with the pump. We cannot undo friction loss. Pressure change is proportional to viscosity. Pressure loss can be defined as the Darcy friction factor times L over D, length of the pipe over the diameter of the pipe, times the density of the fluid and the speed that it is traveling squared, all over 2. And that Darcy friction factor is equal to 8 times the shear stress acting along the wall divided by the density of the fluid and the average velocity squared. This can be simplified to 64 over the Reynolds number for a circular pipe. Taking that change in pressure and putting it into a head equation, so now it's losses that we can add to our energy and Bernoulli equations, that's going to be the pressure losses over rho times gravity, which simplifies to the Darcy friction factor times length V average squared all over diameter times 2 times gravity. Hopefully this portion looks familiar, where this is that kinetic moving pressure or velocity head, right? And then this second portion here, that's the shear stress on the wall. Let's say that we are given some oil with a specific gravity of 0.97 and a dynamic viscosity of 10 to the negative 2 pounds-seconds per feet squared, and it is traveling through a horizontal 1-inch diameter Schedule 80 pipe at a rate of 0.004 cubic feet per second. Find the head loss per 100 feet of level pipe. All right. So all we've talked about so far is laminar. So we need to make sure that this is laminar so that we have equations available, okay? By the way, I did some searching on the internets, and the Schedule 80 pipe has an inner diameter of 0.0798 feet, and we need that inner diameter for the hydraulic diameter for our Reynolds number equation. Reynolds number is equal to, okay, density 0.97 times 1.94 slugs per cubic foot times velocity. I don't have velocity, but I have flow rate. And assuming incompressible, we have Q divided by A is going to be our velocity. So that'll be 0.004 cubic feet per second all over pi over 4 times 1 divided by 12 feet squared. And that will give us a velocity of 0.8 feet per second. So 0.8 feet per second. And then diameter, 0.0798 feet. All over that viscosity of the oil that was given to us at 10 to the negative 2 pound second per feet squared. And we end up with a Reynolds number of 12.01. That is definitely less than 2,000, so we are in laminar flow. That is important, so we can use our head loss equation, which is that Darcy friction factor times length over diameter times average velocity squared all over 2g, where friction is 64 over Reynolds number for a circular pipe for laminar flow. That gives my head loss equation of 64 divided by 12.01 times length, we're doing per 100 feet, all over the hydraulic diameter, times the velocity, and we get 66.4 feet of head loss for every 100 feet of level pipe we have. So what if we have an incline pipe instead of a horizontal pipe? So my flow here I've got drawn along the center line, and then I'm going to have my datum here. So the center line of my pipe now is acting at an angle theta from the datum. Notice that theta is positive when counterclockwise, and negative when clockwise, just like in every other class. Okay, now not only do we have that change in pressure between 1 and 2, but we have the additional gravity pressure of the water in the pipe, or the fluid in the pipe. So we have pressure 1 and pressure 2, as well as the fluid that's in that pipe. So my average velocity in an incline pipe can be the changed pressure minus the weight of the fluid times the radius of the pipe squared, so I should label that, all over 8 times viscosity times the length of the pipe. Putting this in terms of flow rate, we will have the change in pressure, the weight of the fluid in the pipe, pi times the diameter to the 4th, all over 128 viscosity and length. If we don't have any flow in the pipe and we've just got a stagnant closed off pipe, that means that the change in pressure is just going to be the weight of the water in the pipe. In this example, we have a pipeline that is open to the atmosphere on the right end, and on the left end, we're gauged up. That gauge pressure is measuring at 47 kilopascals. The pipe itself is at an 8-degree decline from the datum, and it is 15 meters in length. We want to find the flow rate out of this pipe. Using the equation that we found earlier, flow rate is the change in pressure minus the specific weight length sine of theta. We were given diameter, so pi d to the 4th all over 128 mu L. Okay, the gauge pressure is 47 and it's open to the atmosphere. So the change in pressure is going to be 47 kilopascals. Minus the specific weight. So that is our 876 kilograms per meter cubed density times gravity, meters per second squared. Length is 15 meters. Sine of negative 8 degrees, because we are going clockwise, so that needs to be negative, times pi, and then our diameter is 1.5 centimeters, so that's 0.015 meters raised to the 4th power. Divided by 128 times the viscosity given to us at 0.24 Newton second per meter squared, and then again the length of 15 meters. Okay, everything in here is newtons and meters except kilopascals. So let's get that 10 to the 3rd pascals. All right, now we're on the same units. Plug and chug, our flow rate is equal to 22.4 times 10 to the negative 6 meters cubed per second.